Hello again, and welcome to our fourth mini lecture for the week. In this mini lecture, we're going to talk about something called the Hertzsprung-Russell Diagram, or HR diagram for short. And one of the things that we can learn from that diagram, which is the radii of stars, how big they are. And this material is covered here and there between sections 17.3 and 17.5 in your text. So here are two graphs. One of these graphs is a plot of student ID number versus student scores on homework. And the other one is a plot of student height versus student weight. And I'm wondering if you can guess which is which. Hopefully you would guess that the one on the left is height versus weight, and the one on the right is ID number versus homework grade, because there should be no relationship between the ID, which is randomly assigned, and how well people do on their homework. And the one on the left, you do expect there to be a relationship between height and weight. I bring this up because if you see a trend in a graph, there is often a relationship between the two things. And then as a scientist, we get interested and we say, oh, I wonder what could be causing that relationship. Maybe this is telling us how the world works, how the universe works, how height and weight work. And if there's not a relationship, such as in the graph on the right, we can say, well, that's not going to be very interesting to study. Let's go on to something else. However, you need to be careful. Just because you see a trend, just because you see a relationship, doesn't mean it's a direct cause and effect. For example, suppose the graph on the left is how many ice cream cones are sold at Brahms on a given day versus how many people are at the local swimming pool on a given day. And if you saw that trend, you might say, eating ice cream encourages people to go swimming. And so if you open a new swim center, you might say, I'm going to sell lots of ice cream, and then people will want to come to my swim center and spend money there. But you would be wrong. The real reason for that relationship is a third factor, which is probably the outside temperature. On a hot day, people want to go swimming, and on a hot day, more people eat ice cream. And so these things are related, but it's not a direct cause and effect. So one thing as a scientist we have to be careful with is what's the cause, what's the effect, why is there a relationship, is there some third factor involved? And that's part of the fun of science, trying to figure all this stuff out. Before we go on to talk about the Hertzsprung-Russell diagram, I want to remind you of a couple things we talked about a few chapters ago, and which several of you struggled with because it's a hard concept. And that dealt with blackbody radiation. The first thing we talked about was Wien's law. And forgetting about this equation, let's just focus on the bullet points at the bottom. If you have something that's glowing because it's hot, the hotter it is, the shorter the wavelength at which the spectrum will peak. And since short wavelengths are bluer in color, the hotter something is, the bluer it's going to appear. Conversely, the cooler it is, the longer the wavelength at which the spectrum peaks, and so the redder the object will look, because red is a longer wavelength than blue. So let's remember that. Hot things are blue, cool things are red. The other thing we talked about was the Stefan-Boltzmann Law, which, again, let's look at just the two bullet points. The hotter an object is, the more energy it emits. The cooler it is, the less energy it emits. And second, the larger the object is, the more energy it emits. And the smaller it is, the less energy it emits. So the total energy emitted, the luminosity, L in this equation, is related to the size of an object, in particular for our interest, a star, and also the temperature of the object. So these are things that we talked about a few chapters ago. So now let's talk about the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is a plot, and on the x-axis we put the temperature of a star, and being astronomers we plot it backwards. We put the hot temperatures on the left and the cool temperatures on the right. The reason for that is before we knew exactly what the temperatures were, people plotted it based on the color and what the wavelength was of the peak of the spectrum. So blue things got plotted on the left because that's a short wavelength. Red things got plotted on the right because it's a long wavelength. And but since we know that temperature and color are related, blue things are hot, red things are cool. So that's why it got plotted in this funny way. And in the last mini lecture, we also learned about the stellar spectral sequence, OBAFGKM, and we learned that that tells us also about a star's temperature. O stars are hot, M stars are cool, and the rest scale in between. So in reality, we can plot any one of those three things on the x-axis. The temperature, with hot on the left and cool on the right. The color, with blue on the left and red on the right. Or the spectral sequence, from left to right, OBAFGKM. On the y-axis, we plot the luminosity of a star, how much energy it's emitting. And going back to the first mini lecture, this would be the absolute magnitude, not the apparent magnitude, the absolute magnitude of a star. Or its luminosity. Here we're just plotting it in terms of the sun, where 1 is how bright the sun is 10 times brighter than the sun, 0.1 is 1/10 the brightness of the sun, and so on. So in this axis, we plot brighter objects at the top, fainter objects at the bottom. So if we had absolute magnitudes, that would mean the most negative numbers at the top, 0 somewhere in the middle, and big numbers like 10 or 15 down near the bottom. Because smaller numbers, more negative numbers, mean a brighter star. And if we plot the stars on here, such as in this diagram of several stars in the sky, we see that there are a few patterns. First of all, you see the stars just don't appear everywhere. They appear in just a few places. Most stars occur on a line that goes from the upper left to the lower right of the diagram. So from bright, hot blue stars to faint red, cool stars. This is called the main sequence. So we see this pattern, and we may wonder why that pattern's there. That's something we'll have to look into. We also notice there are a handful of stars that are up here in the bright and cool category. And we've got one star, and there are a few others that aren't plotted here, but just a handful of stars that are down here in the faint and hot category. So, a few faint and hot, a few bright and cool, and most that go from bright and hot down to faint and cool. So this summarizes what we've talked about so far. We're plotting stars' temperatures versus their luminosities. The x-axis can be temperature or color or spectral type. The y-axis can be luminosity or absolute magnitude. And one thing that we can instantly begin to do is realize that, from what we learned about the Stefan-Boltzmann Law, this diagram can help us determine a star's size. Because if we have something that is faint and blue, well, that means it's hot, and hotter things should be brighter. So if it's faint, the only way to have something hot and faint is to have it small. And if we have something that is cool and bright, cool temperatures would mean a fainter star. So the fact that these are very bright means that these must be very big stars. So by looking at where an object is in this diagram, we can see that some of these stars must be very small, and some of these stars must be very big. So as I said before, most stars fall on a line in the diagram that goes from bright and blue to faint and red. We call this the main sequence. It gets that name because it's a sequence of stars, and most stars lie along it. And we will need to talk about why most stars lie along this. That'll be next week. The bright red stars are called red giants and red supergiants. They get these names because they have to be large in radius. So we've got giants and we've got supergiants. As you might guess, and you'd guess correctly, supergiants are much bigger than giants. And the faint blue stars we call white dwarfs. White because they're white hot, dwarfs because they must be very small. So these are the three main types of stars I want you to remember: white dwarfs, main sequence, and red giants. And I'd like you to be able to identify those on a graph like this. So as we already said, the Hertzsprung-Russell diagram, we can read off the radius of the star, that as you go from the lower left to the upper right, you go to larger stars, from small stars to large stars. These diagonal lines here are lines of equal radius. So stars along these lines would have almost the same radius. And what you can see is that main sequence stars, they vary somewhat in radius, but not a lot. They go from about 10 times the radius of the Sun up for the bright blue ones, down to about 1/10 the radius of the Sun, down here for the faint red. The white dwarfs are all very small, about 1/100th to 1,000th the radius of the Sun. And the red giants are 100 or even 1,000 times the radius of the Sun. So let's look at the relative sizes of stars. I'm going to show you some pictures that compare star sizes, and these are actual relative comparisons. Now the scale will differ from picture to picture. Let's just go ahead and see. So let's start with main sequence stars. In the lower right, we have the Sun. If the Sun were this big, it's a G2 star, as you can see. If the Sun were this big, then other main sequence stars, Altair, which is an A star, Vega is an A star, Regulus is a B star, Achernar, which I'm not even sure where that is. I think it's in Scorpius, but I'm not certain. It's a B star. And you see that as we go to hotter stars on the main sequence, they get larger. And that egg shape that they seem to get as they go up, that's because the hotter stars often are spinning faster as well. And if you spin really fast, you get more egg shape instead of spherical. But even if we ignore that, you see that as you go up, you get to larger stars. But Achernar, it's not crazily larger than the Sun. All right, now let's compare the Sun to red giants. So the Sun is right there, 1 pixel in size. And a couple of stars in the winter sky, Castor and Pollux. They're in the constellation Gemini. Castor's a main sequence star. It's a star sort of about the same size as Vega. So you can see that's a main sequence star the size of Vega in the other picture. And then as we go up to the giants and the supergiants, you see that these stars get absolutely huge. Arcturus is a red giant star that's visible in the spring sky. And you can see roughly how big it is in comparison with the Sun, much bigger. However, it's dwarfed by Aldebaran, which is a red giant in the constellation Taurus, the bull. But that one is dwarfed by Antares and Betelgeuse. Antares and Scorpius, Betelgeuse in the constellation Orion. Look how big Betelgeuse is. If this were our own solar system, Betelgeuse would completely swallow all the planets out to and including Jupiter. You know, the Earth would be gone, Mars would be gone, the asteroid belt would be gone, all the way out to Jupiter. It's over 1,000 times larger in radius than the Sun. Absolutely huge. That's why they get the name supergiants. Now if we go the other direction toward low mass stars, here is a cartoon of the Sun. So again, we've rescaled here. Sun looks pretty big in this cartoon. If we go to the lowest mass stars, those faint red stars, we see that they're much smaller than the Sun in radius. And then we get to things like brown dwarfs, which are not massive enough to be stars, and the planet Jupiter, and there's the Earth for comparison as well. So the lowest mass stars are a little bigger than the planet Jupiter in radius. Finally, we get to the white dwarfs. So here's yet another diagram, the radius of the Sun here, and a white dwarf is comparable in size to the Earth. And so what you see is that white dwarfs are extraordinarily small. That's why they're called dwarfs. So compared to the Sun, a white dwarf is minuscule, but compared to Betelgeuse, the Sun is minuscule. So, a summary of what we've learned in this mini lecture. The Hertzsprung-Russell diagram is a plot that plots temperature on the x-axis versus luminosity of stars on the y-axis. Stars don't appear randomly on the diagram, but they're mainly found in one of 3 places. The main sequence, which goes from bright blue stars in the upper left to faint red stars in the lower right, and that means bright hot stars to faint cool stars. Red giants, which are in the upper right, they're bright but they're cool. And white dwarfs, which are in the lower left of the diagram, they are faint but hot. And the Hertzsprung-Russell diagram can also tell us about the relative radii of stars. And smaller radius stars are in the lower left, while larger radius stars are in the upper right. So this completes our mini lecture on our introduction to the Hertzsprung-Russell diagram. Go ahead and complete the response to this mini lecture and then continue on to our final mini lecture of the week.